Hello and welcome to our lesson on polynomial functions. In this lesson, we'll delve into how we can increase the exponent of equations and relate this to the material we've covered previously. First, we will understand the concept of increasing the exponent in equations. Then we will look at how we can graph quadratic and cubic equations and the key features of these functions. So far, we've built a strong foundation by discussing the properties of straight-line graphs, which has given us a solid grasp of basic polynomial equations, particularly those with an exponent of 1. With this solid groundwork in place, we are ready to introduce the technique of increasing the exponent in equations. While straight-line graphs are useful, sometimes we encounter situations such as projectile motion in physics, where the relationship between variables is quadratic, requiring us to work with equations where the exponent is 2 instead of 1. In our previous lessons, we worked with equations that primarily had an exponent of 1. But remember, we usually don't write to the power of 1, because an x on its own implies this, so there is no need to actually write the 1. These are what we call linear equations, and you've already seen how they form straight-line graphs. Today, we are shifting our focus to polynomial equations where the exponent is greater than 1. When we talk about increasing the exponent, we're essentially moving from equations like y equals x to more complex ones, such as y equals x squared or y equals x cubed. These equations are known as exponential equations or polynomial equations of higher degrees. To increase the exponent in an equation, we essentially raise the variable to a higher power. For example, a linear equation such as y equals x has the highest exponent of 1. In a quadratic equation such as y equals x squared, the highest appearing power of x is 2, leading to a parabolic shape when graphed. In a cubic equation such as y equals x cubed, the highest appearing power of a variable is 3, resulting in a more intricate curve with possible inflection points. We know that the graph of y equals x is a straight line. Now consider how the graph of y equals x squared is different. Instead of a straight line, it forms a parabola that opens upwards. In y equals x, the graph crosses the origin 0, 0. For y equals x squared, the graph also passes through the origin but has a turning point at that same spot. As we increase the exponent further, the shapes become more complex, introducing more intercepts and turning points. Let's understand the general forms of these graphs. Quadratic graphs form U-shapes called parabolas. The basic quadratic graph y equals x squared opens upwards with its vertex at the origin 0, 0. If the equation were y equals negative x squared, the parabola would open downwards. Cubic graphs have more of an S shape with one inflection point. The graph of y equals x cubed crosses the origin and has an upward curve on one side and a downward curve on the other. A negative coefficient, such as in y equals negative x cubed, would flip this curve. Visualizing these graphs is critical for understanding and solving the equations. If you are faced with a quadratic or cubic function to graph, start by plotting several points, which can help you trace the shape of the graph. Also identify the key features by looking for intercepts, turning points, and symmetry, such as in the shape of a parabola. For example, suppose you need to plot y equals x squared. Start by writing out values of x and calculating the corresponding values of y. In this case, we just need to square x. We therefore find points like -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4, and so on. If we then plot these points on the coordinate grid, you will see the parabolic shape forming. These points can be connected to form a parabola. Now suppose you need to plot y equals x cubed. Start by writing out values of x and calculating the corresponding values of y. In this case, we just need to cube x. We therefore find points such as -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. If we then plot these points on the coordinate grid, you will see the cubic curve forming. These points can be connected to form the graph. By understanding the shape and features of these graphs, you can more easily tackle problems involving higher degree polynomials. In summary, While polynomial equations represent a step up in complexity from linear equations, they still follow predictable patterns that can be understood visually and algebraically. As we practice, you'll gain confidence in manipulating these equations just as you did with linear ones. In today's lesson, we explored the concept of increasing the exponent in equations, moving from linear to quadratic and cubic equations. This transition allows us to solve more complex algebraic problems by raising the variable to higher powers. We compared linear equations, which form straight-line graphs, to quadratic equations that create parabolic shapes, and cubic equations that result in more intricate curves. We related these higher-degree polynomial equations back to our previous understanding of linear equations, noting the differences in graph shapes, intercepts, and turning points. Watch the rest of the GCSE Maths course at Sophos Education.